Okay. So this begins chapter 13, section 5. And we're going to be talking about colligative properties. Okay. So colligative properties is basically a term that means that these are particular properties, or 4 properties, of a solution that are dependent on the amount of solute. Dependent on the amount of solute. Okay. So they will change. The amount of change in these properties is going to be dependent on how much solute we can get into solution. We're going to be looking at vapor pressure lowering, which is going to be the first one. Whoop. Down arrow for lowering. You'll often see vapor pressure abbreviated uppercase P and subscript VAP for vapor. We're going to look at boiling point elevation, freezing point depression, and then osmotic pressure. So those are the 4 we're going to be focusing on. What's that? Yep. My screen is slightly different than yours. There we go. Okay, so first thing, let's think about vapor pressure. So you talked about vapor pressure in 12 to 10, right? At the end? Okay. So the vapor pressure is the amount of pressure exerted by a gas in a container or in a vessel of some sort. It's only the vapor contributes to this pressure measurement. And it's because we have molecules in the gas phase. And so they're hitting the walls of the container, they're moving around, hitting the walls of the container, causing this pressure. The molecules that exert the highest vapor pressure are molecules that are more volatile. So let's write that term. You've probably seen this, volatile. It means something that can easily enter the gas phase. Okay. If you're thinking about molecules that easily enter the gas phase, would you expect them to have high intermolecular forces or low intermolecular forces? Low. Yeah. So low intermolecular forces meaning they're not bound very strongly to each other, the molecules. And so usually, like you said, we have low IMFs, intermolecular forces, in something that's very volatile. Okay? If something is non-volatile, it means it doesn't easily enter the gas phase. Now, at high enough temperature, we can make a lot of things enter the gas phase. So what this easily is referring to is typically at room temperature. So solids, for instance, don't typically enter the gas phase very easily, and we would expect them to have high intermolecular forces. Okay, so all that intermolecular forces stuff, we went over, again, playing another role here. All right. So this figure that we have here is showing that showing the example of how molecules enter the gas phase and exert pressure. If we have a flask that is completely evacuated, has a total pressure of 0, and then we add to it some amount of a volatile liquid, and in this case it was ethanol. The molecules begin to vaporize, and eventually they come to equilibrium, where there are molecules entering the gas phase at the same rate that they're going back into, they're condensing back into the liquid. Again, all of these molecules are exerting pressure on that thing, that flask, and so we have a reading for our vapor pressure. But what happens if we add a solute to a solvent? Well, we get what we call vapor pressure lowering. So the vapor pressure of a volatile liquid, a volatile solvent, is lowered by adding a non-volatile solute, something like for example, a salt, or some other molecule. Sugar is a great example. We're going to talk about that with many of the colligative properties. It's not a salt, it doesn't form ions, but it's not very volatile. So why is the vapor pressure lowered when we add something? Still solvent in there, right? Any thoughts? What's that? More chaos? Not quite. Yeah? Less surface area. Yeah. Oh, yeah. Yeah. Exactly. So let's imagine we've got these spheres represent, the blue spheres represent solvent molecules, the volatile solvent. The red spheres represent solute, non-volatile. If we're thinking about surface area, here's without solute, right? We've got lots of the entire container, the entire surface. We're able to have solvent molecules at that surface, entering and exiting the solution to form equilibrium. We add some solute molecules. They're taking up space along that surface. And the more solute molecules we add, the more area they take up, and the less solvent can escape into the gas phase, and so the vapor pressure is lowered. And again, for salts and non-volatile solutes, they don't enter the gas phase. Okay, so they're not contributing to the vapor pressure. So, let's see. Vapor pressure is lowered because less surface area. Oh, I'm using another shorthand. Okay, so less surface area for evaporation, that's what that's supposed to say, and condensation or condensing. Does that make sense? Okay, now, I want to point out something in your textbook. There is a very important section of your book, and it's a little less hidden in the ebook, which I'm very thankful for. But it's a closer look section. It looks a little bit different than this now. But it's going to talk about what happens when you have two or more volatile components. So let's say we have our solvent, which is volatile, and we add a solute, which is also volatile. What happens? And so when we have a mixture, let's say we have a mixture, wait, let me make sure I don't have another slide. We have a mixture of acetone, which is volatile. We're going to call that A. And we have a mixture of acetone with toluene. We saw toluene the other day. I spelled that really wrong. toluene. We're going to call that T. Both acetone and toluene are volatile. So they are going to follow what we call, this Rayold's law for a mixture. Let me write Rayold's law for vapor pressure lowering. I guess I kind of avoided that last slide. Sorry about that. Okay, Rayold's law says that the vapor pressure of a solution is equal to the mole fraction of solvent, that's a unique unit right here, times the vapor pressure of pure solvent. So I'll write these terms out. So I'm still going to do PVAP for vapor pressure. So vapor pressure of the solution is the vapor pressure of the solute plus the solvent mixed together. This, I think it's, so this mole fraction business here is mole fraction of solvent. Okay, I think in our units slide for the concentration units, we saw mole fraction of solute. Okay, so watch that. Rayold's law is mole fraction of solvent. Easy mistake to make when you're doing calculations. And then the P0 solvent is the vapor pressure of the pure solvent. Okay, which will be the value you could look up. And it'll be at a given temperature. Okay, so now this is for if you have a non-volatile solute. If you have a mixture with two volatile components or more, we end up with this equation. Let me just highlight the important part here. All right. Mole fraction of solvent, mole fraction of component A times the vapor pressure of pure component A plus the mole fraction of component B times the vapor pressure of pure B. Okay. All right. We don't need to worry about this A and T. I'm going to skip that. Questions on it? Yeah.
Can you go back to the Rayold's law?
Yep. For sure. Anything else? Let's do one example. Okay, so this says a solution of heptane and octane has a total vapor pressure of 66.31 torr at 40 degrees Celsius. The vapor pressure of pure heptane and pure octane are 91.96 torr and 50.92 torr respectively at 40 degrees Celsius. What is the mole fraction of octane in the solution? So a couple of things here, context clue wise. If you didn't know that heptane and octane were both volatile, totally understandable, but you can get that from the problem because they both have a vapor pressure. If you have a non-volatile solute, you're not going to be given a vapor pressure for that solute. Okay. Should we work? You want to work on this yourself? Or you want me to go? I figured. It's Friday, right? All right. The vapor pressure of pure heptane, we're going to do H for that, subscript H, is 91.96 torr. Do you guys think that units matter in this problem? Yeah? So could we use atmospheres? Bar, whatever else, favorite pressure unit. As long as they're consistent, we're fine, okay? So if everything's given in torr, use torr. Vapor pressure of pure octane, we're going to do subscript O for that, is 50.92 torr. Total vapor pressure. Again, going back to our Rayold's law for two volatile components, we're going to have the mole fraction of heptane times the vapor pressure of pure heptane plus mole fraction of octane times the vapor pressure of pure octane. So the problem says, what is the mole fraction of octane? That's what we're looking for. We know everything except that, I believe, right? We have the total vapor pressure, 66.31. We're given the vapor pressure of the pure. Oh, we aren't given the mole fraction of heptane, are we? Okay. Oh, right, this is a good one. I forgot. Okay. Let's write this then. We want mole fraction of octane, and we know P total, P naught octane, P naught heptane. Okay. Now we need what? We need to know something about mole fraction. We have two things and we're mixing it together. What's the, how do I ask that? Let me just write the answer. 1 is equal to the mole fraction of the heptane plus the mole fraction of the octane. Okay? These are fractions, right? So the two components make up the whole. That's what that's saying. Whatever amount of heptane plus whatever amount of octane is equal to 1. So we can actually solve for mole fraction of octane. It's going to be equal to 1 minus the mole fraction of heptane. And now let's plug some values in. Might be okay. Total vapor pressure 66.31. I'm going to leave off my units. Equals mole fraction of heptane times the pure heptane vapor pressure 91.96 plus the mole fraction of octane, which is 1 minus mole fraction of heptane. Times the 50.92. Okay, now we get to do algebra. I'm going to let you do that on your own. I'm going to sort of fast forward a minute here. So we're going to have 91.96 mole fraction of heptane plus 50.92 minus 50.92 mole fraction of heptane. Do a bit more solving. Feel like equals 66.31. There we go. Do a bit more solving. Okay, do more algebra. And so we're going to end up with 0.375 equals the mole fraction of heptane. I skipped a bunch of steps there. Okay. Well, we asked for mole fraction of octane, right? So the mole fraction of octane is going to be 1 minus the mole fraction of heptane. And that's going to be equal to 0.625. What are my units there? Yeah, it does crack. It's mold friction, right? So it's moles over moles. There's probably a more efficient way to do that, which would be to solve for mole fraction octane first, and then plug that in instead of the way I did that. Either way, gets you there. Questions on this problem? Real quick, I want to do boiling point elevation, just kind of quickly. And no, I don't. We'll stop.